So hello everybody. I welcome you to my webinar today. My name is Rainer Schramm and I would like to show you today some examples for using correction models in XRF. This will happen after two other webinars I already have given in the past, and one was for theoretical alpha correction, fundamental parameter use, and the second one was an overview about all correction models. So if you want to know more about theory, then I present today, then these two webinars are really good to have a look at. So today I'm just giving the examples which were missing in one of the last webinars because time was just limited. Yeah. So I would like again to start with the measuring principle. So what is XRF? Then talking about the relationship between our intensity we measure and the concentration. Then I give you an example about theoretical matrix correction, empirical matrix correction, and the strategy you do when you just start with an application. You see you might need a matrix correction, but you're not sure. And there I want to give you some ideas how you can proceed there. So we all start with the origin of X-ray fluorescence, and X-ray fluorescence is produced by irradiating your sample with an X-ray tube normally, and then some of the inner electrons will be taken out of your atom. That means the atom is ionized. Then other electrons from higher levels will fill up that gap, and this could result into fluorescence radiation. So if we see it here, let me say the inner shell is ionized. That means the electron is taken out. Then there is a possibility that from higher levels, electrons will fill that gap, and then the corresponding radiation is sent out as fluorescence radiation. And generally, we distinguish two types of lines. And one series is called the K lines, and the other series is called the L lines. There might be also M lines additionally. And they always come in a certain pattern. And what is important for me today is when we talk about intensity, then in the calibration model, where is this intensity coming from? And in case of wavelength dispersive XRF, it's always the height of the line. Like here, for example, an iron car alpha. And if you use energy dispersive, it's mostly the surface of the peak, which is then used as source for the intensity. If you use L lines, then it's either the L alpha or the L beta you use as the most intense lines there to get either the height or the surface as intensity. In the end, you will have the relationship. That means you measure your intensity and you have a set of standard materials, and the idea is to correlate both. And so you will have a diagram like this. So the intensity is in relation with your concentration, but in the most XRF software packages, this is presented inverse. And this is why I mentioned this here, so that the intensity is on the x-axis and the concentration on the y-axis. And so that then every correction or coefficients we have are expressed also in concentrations. But we will see this later. So here you get an overview about all the correction models we have in XRF. And of course, the easiest correction model is if you use no correction. Yeah? So you just have your relationship between intensity and concentration, and with a straight line, you establish the two coefficients, and you get your calibration. That is, of course, the ideal case, and we all wish that we can use that and we don't need any correction models. But in case, and this is the normal case in XRF, the elements are all influencing each other, then your curves, your calibration line starts to be curved for each element, and there will be some interactions. And then you need matrix corrections. And there are different models. So either you describe your relationship between concentration and intensity fully theoretical. then it would be fundamental parameter. If you just say, I have my linear approach and the matrix correction, I just calculate as a factor, then we talk about a matrix correction, or you just use, like very often in analytical chemistry, an internal standard. So you use the Compton scattering peak as an internal standard to do the matrix correction. We could split that further. That means that our matrix factor could be either calculated from the theory, also called as variable alphas or as constant alphas, or you calculate it empirically based on standard materials. Yeah? So these are the two ways. So this case here is a bit comparable to this case, just a different approach, but the result will be quite the same. But now let us start to observe the easiest way to do correction. That means no correction. So that means in the start, we will have, it will look something like this. You measure your standard materials, you have your intensities, you have your concentrations, and by a linear regression, you will establish your calibration line, which in the end will give you a coefficient for the slope and an absolute offset for this kind of A0. But in the real world, we often have situations like this. That means, for example, you want to do a production control and all your standard samples are coming more or less with the same values, so you get more cloud. And then if you would establish a linear regression, the curve could, or the line could look like this. That means it's either like this or it could be even negative, but what we want to see is that one. So here you see already the influence of allowing to calculate the offset A0 or not. So in this case, I would always recommend you that you do not allow the calculation of A0, so that the 0 point is also part of the calibration. So that means 0 concentration means 0 intensity. There are some software packages around which do not allow this. So it's always A0 is calculated. Then you have a problem. Then it will look like this. And then you have to look for a sample which gives a point in that range so that you can force your curve to go through 0. This is not so easy. And like I said, it's depending a bit on the software package, but you should never work with such a calibration line. It should be always touching the 0 point. There are some rare cases where you could use a quadratic approach. And I would tell you, be very careful in using this, because there are, it's a high risk that you overcorrect your calibration. And I will give you here 2 examples where I would use it. And this, for example, here is silicon and oil. And what we observed here is that with increasing concentration, there is more intensity measured. So you see, it's a bit curved up here. There is no real explanation for this. So it must be the sample which behaves like this. So it could be either a dilution problem, or it could be that here the silicon is sticking a bit to the wall of the sample cup so that we don't see all the elements. But there is no real explanation, and then you have to be really careful in using this. But here you see the effect. If you would use a quadratic approach, you have about a factor 3 better regression line. Another example, now more serious, is zinc in oil. And then we have about 10 times higher intensity than in this silicon case I presented you. And here we really have self-absorption. So here I can explain why we have a curve. That means as more zinc is in that sample, as more zinc is absorbing zinc and taking away a bit of the signal. And this is why I get a curve. In this case, I would say it's allowed to use that quadratic approach. And you see that you here have about a factor 10 better fit to the line. In all the other cases where you are not sure if this makes sense or not, please don't do it. Don't use a quadratic approach if you are not sure, because there's always a big risk that you overcorrect your calibration model. Okay, now let's talk about the first correction. So we talked then about matrix correction, and the question is why? Why do we need such a correction? And I want to explain this here with the example chromium. So let us assume we have a sample just with chromium. And this would give then the blue line here. This is the blue chromium line. And then we have the case that the same sample contains iron. So the iron is additionally exciting chromium, and this means we get a higher chromium peak than expected. Another example is that the same sample contains titanium, and the titanium is taking away a part of the fluorescence radiation of chrome, so the signal is decreased. In our calibration, this would look like this, that if the titanium is present, we lose intensity, so the point is on the left side of our line. In the iron case, it is increasing the chromium intensity, so we're on the right side. These 3 points have no interfering elements, so that's why they are ideally on the curve. So our intention is now that this disturbance by either iron or titanium to our chromium signal is corrected by a so-called M, a matrix correction factor. Yeah, and with this M, we would like to change the intensity in a way that both points are just at the line where the green point is. And this is the so-called matrix correction we want to do. We have there 2 possibilities. So either we calculate this M totally from theory. That means we say we use the tables and databases which are well known for XRF. And in this case, we can calculate this matrix factor for our sample. Or in a second way, I use a set of standards where I then calculate my M from that. But let us first see how we do that, or an example, how this will be presented in the real world. Yeah. So here you see that this is our M factor, and I make it really short with this formula. And this M factor is then containing this alpha correction, these alpha coefficients, which are calculated from the mass attenuation coefficients. But in an example, this looks like this. I have here a calcined cement, 1 gram, and 8 gram flux, and I'm making a fuse speed out of it. Fuse speed is homogeneous, is considered as ideal sample, so it could be completely described by theory. Yeah. So all the theoretical models, either by fundamental parameters or theoretical alpha corrections, will work perfectly on such a sample. But why? Because I can measure all elements which are in the sample, plus the oxygen, which I cannot measure, is linked to the elements. So that means I can describe 100% of my sample. And if I then let it calculate, I will get a sum around 100 and the good results for the sample. So the software has no problem. And the flux I'm using, I'm also describing. In this case, it is FX-X65, which is 66% tetraborate and 34% metaborate. But if I only make now the trial that I tell the software I use a different flux, just 100% lithium tetraborate, then you see already the influence. I have given a wrong information, and immediately my main component has added an error, and you see also at the sum that we are a bit off from the real values. So the theory considers always that all parameters you give are correct. This is important because only then you can use it. And now we make some more tests. That means we just recalculate our sample. So I just express this one as element and take out all the oxygen. You see that in total we have 36.42% oxygen and all the rest are element. If I don't tell the software that this oxygen is in a sample, you see there's a big error now on my main component. So it's 5% off from the real value. And if I do now another approach that I say, I tell the software that there is so much oxygen inside, immediately I'm back to the real theoretical value. And this is what I want to show here. You can always use the theoretical matrix correction when you are able to describe your sample 100%. In the moment, you're just interested only in one element and you don't know all the others, you can only work with empirical corrections. And this will be now our next approach. I want to show you how you do that. And there are two approaches. One is based on intensity and the other is based on concentration. Intensity makes sense when you just want to correct the element of interest. So you're just looking on chromium. You have no information about all the other elements. You know there are elements. You know they will disturb your line. And this is why you can use intensity corrections just to correct for the matrix effect. But if you know the other elements, I would always use a concentration-based model, because concentration means it's already matrix corrected. So you add one more information in your system. So that's why the concentration models are always preferred, but you only need to give the elements of interest and the elements which are disturbing. The rest you can ignore. Yeah, so this is the advantage to the theoretical models. You only watch the elements you need for your model. And this is how it looks like then. Again, we have our M factor, and the M factor now is in the M factor, the coefficient of the matrix correction is calculated by your set of standards you will present to the system. I give you an example now. We have here established a FLUXANA training set for learning how to calibrate a wavelength dispersive XRF. And so if you get this set from us, and together with the online training course, you can learn all these steps, how to calibrate an XRF in an online course. And in this set, I have 3 samples where the kappa value is known. So one has 0, one has 0.246, and one has 0.17% of kappa. But in one of these samples is also chromium, in the other not. And if I do now a calibration with these 3 samples, you see how it will present, that they do not fit on a line. Yeah. So we have the one with the high chromium value. It's really off, because this will decrease the kappa intensity because of the presence of chromium. So this means to get all 3 on a line, I need a matrix correction. And then if I would do that, that means I will allow the software to do a matrix correction from chromium to kappa. Then this coefficient is calculated. And if we just look how the software is doing this, you remember this is this M factor. So this factor is calculated by your calibration set. This is the chromium concentration in your standard. And then both together give here a factor different from 1. The intensity is changed and the point is going to the line. While the other 2, which do not have any chromium, you see here the concentration is 0. So this gets 0. So here the factor is just 1. So the intensity remains unchanged. And the same we have for this FLUXANA 2, where also no chromium present. So this is how an empiric matrix correction is working in the routine. That means with a standard, you establish your matrix correction factor from one element to the other. And then in the real world, the concentration which is found then in your sample is used together with this factor to correct the intensity so that the points are going back to the line. Okay, let's take another example from the real world. That means here I have some slag samples that were prepared as press pellets. And I would like to calibrate aluminum oxide in this set. And this is my first approach. So I have here some standard samples, and here in this range they fit quite nicely to the line. But here I have a kind of a scattering of the points. The raw standard deviation for this curve is about 2.67%. The question is, can I improve this now by adding any matrix correction? So the first thing I will do is I investigate this set of standards. So here I have the table, 6 slag samples. I have all the values with all the elements. And now I have to check, is there a reason that some of these elements make matrix disturbance to other elements? So what do? I first look at the sum. So is the sum around 100? I could, of course, also think about a theoretical correction, because the sample is 100% described. However, there is one with 90%, and the big question is, what is that? What is missing here? It could be that one element was not reported, and this is 10%. 10% is a high value. So probably you have to make further investigations about the samples to find out what is the problem. You see, this is the 5.1, so this point in my curve, and there are no other points, so I have no comparison if this is a deviation or not. So I can just take it like it is for the moment. Yeah. So with such a sample, I can only make an empirical correction because it's not 100% sure if all these results are correct. The next thing I will do is I look for major components. So what is major here? Beside my aluminum, we have high calcium in there. We have magnesium oxide and we have silicon oxide. So these are the main concentrations in these standards. So if there is a matrix influence, it could be always come from this three. Yeah. So this is really here the case. And so what I will do, I will always start to try with the highest concentration of a disturbing element to check whether this will change the situation. And that means if I introduce the calcium, my standard deviation is decreasing from 2.67 to 1.75%. And this is because this point is jumping there and this point is jumping there. So they are much closer to the line than they were before. So this is already a good step further, and I would say this is worth to do that correction. If I check all the others, I can tell you that nothing will change the situation. It will always be in the range of 2.67, never go to 1.75. So the calcium is the only correction which really makes sense. In this case, I could fix that. And then I can check if a second correction also makes sense. So I just give you one example. I use then the chromium additionally, and you see nothing happens. The 175 just remained 175 if I add chromium or not. And then this is for you important, take it out. Only use a correction if you get a significant improve in the error. If not, leave it away, because you always have the risk of overcorrecting the model, and in this way producing really wrong results when you use this for unknown samples. Yeah, and so it's a bit trial and error, but you always must make sure that you have a significant effect. Otherwise, leave it and just take the curve like it is. So last but not least, I would like to present you that Compton correction model, and there we use the Compton peak to correct for the intensities for the matrix effect. And here is one example. So I have polymer disks, one from ABS, one from PE, and I look on the Compton peak of the scattered molybdenum X-ray tube line, and you see that the Compton peak for the ABS is different than for the PE. And the reason for that is that ABS contains nitrogen as carbon and hydrogen, while PE only contains carbon and hydrogen. So the matrix is different. And this Compton peak just shows that, yeah, it just represents the whole sample. And this is mainly consisting out of the polymer matrix. So even if we can't measure the single elements here from the organics, we can see the effect in the Compton peak. And if I then calibrate the elements of interest, and here we have this heavy elements, chrome, chromium, cadmium, mercury, and lead. And then they are all, the intensities are all normalized to this Compton peak. And then I'm able to measure both matrices in one calibration. Yeah? And this is a classical example for Compton correction. And it is mostly working well if the elements lines are very close to the Compton peak. As far away these lines are, as more difficult it will be. Yeah. So this is a general rule, and yeah. So this is already the list of examples I would like to present you today, and that means I explained you the measuring principle. We talked about the signal and concentration ratio, and I explained you that the standardless calibration approach is only possible if you can describe your sample 100%. If not, you have to go by an empirical correction to get your calibration under control. And I would like also to announce our next webinar, which is then a real sample preparation webinar, that you are welcome to join this as well. Okay, thank you very much so far. And now I will have a look on the questions in the chat here. Here is the question. Our instrument has a correction model referred to as the classic model. Which type of correction is that in the tree you showed as one of the first slides presentation? And as a second sample, is there some material to find where more examples of where a quadratic regression model could be used? Or how do I find information on how to calculate or realize where it's usable? So a quadratic model, I would really only use if you have no matrix correction, and if you have more or less single element standards, which then show a quadratic relationship on higher concentration. In all the other cases, you should use your matrix correction model to correct for it, and not the quadratic. Yeah, so quadratic is really a very rare case. You should use only for this kind of single element standards, where at higher intensities you show this effect. The classic model, I can't tell you because I remember it, but I don't know in which software. So you have probably to give me some more ideas. Perhaps you can offline send me a screenshot of your software, and then I might remember what kind of model this is. Yeah, so perhaps I can help you in this way. There's another question. In some of the examples, the regression line does not go through zero. Why is this? It would mean that when your concentration is zero, you have an intensity. And this is also so-called a blank value. It could be, for example, if you have no background measurement, so you just measure your gross intensity, then of course, if you have zero concentration, you still have an intensity, and then you would establish an offset in your calibration. Yeah? Or you have established a background, but your peak is sitting on a slope, so you could even have negative offset or positive offset. So another question, where can I determine what elements are corrected against? You always watch your element of interest, and then you see if the points are fitting to the line. If this is not the case, you look for the point which is the farthest away from the line, then you take your standard table, and then you investigate, is there any reason for that point that it's off? And if you see, yeah, for this standard, there's one element in a very high concentration and all the other standards don't have it, you have an indication that you should try to correct for exactly that element. This is always the strategy, how you can find out what element is really influencing your other calibration line. But you always have to make sure that the concentration is high enough. Only high concentrated elements make matrix disruption. Trace elements don't do that. There's another question. Can we use Compton peak when we do calibration for light elements, calcium and silicon? Well, then mostly the Compton peak is quite far away. So it's probably not really successful if you use that. You can always try and you will see if this gives you any improvement, but I would say probably not. Yeah. Another question, comment, assure, a moment, this is in French. Demon. In English, the question is more or less, how can I make sure that I can correct my XRF, and how can I choose the correct method? Of course, this is a very, very general question. In the end, like I said already, you have to look on your standards, and you have to see together with the calibration lines, how is this approaching? Yeah. And perhaps sometimes it's a good start to use the theoretical models to see if you are able to correct for this kind of application, because then you see if this is the right approach. If that is not working, then of course you have to do it empirically. And in all these cases, you have to understand what you are doing, and you have to study really your calibration set to get an idea what is going on. I mean, you can always send me these kind of questions offline by email, and I will try then to give you some help. So this is always an option. Yeah, don't hesitate to send me some problems of your daily work. I'm always happy to have a look on it and to give you some help. So, any more question? Yes. There is someone is analyzing bauxite. We made a calibration with 10 view speeds, and we can see an offset for 3 samples. They stick out from calibration line. What could be the reason, since they are fused and no mineralogical effect? What you should do is that you look on the calibration table, and if for these 3 samples there is any kind of difference for the other elements, yeah. So I'm expecting that you look on one element like aluminium. Aluminium is one of the major elements in bauxite, and then you say 3 points are off. So you check why. What is different from these 3 points? Is there a high silica content, for example? Is there a high iron content? And this would be then an indication how you can correct for these elements. Because you say here there is no mineralogical effect. That is correct, but it could be still a matrix effect. That means that there is another element in a higher concentration, which then makes these 3 points to be off the line. Okay, any more questions here? I can't see them in the moment. So it looks like I have answered all your questions. Like I told you, if you have some more questions, just send it by email. I'm really happy that you asked so many good questions, and I thank you very much for this contribution, and it's always really a pleasure to work with you. And yeah, thank you very much all together, and I hope seeing you again in one of our next webinars. Have a nice day, and yeah, see you soon. Thank you very much. Bye-bye.